The last topic we'll be looking at here in Chapter 7 is the idea of electron affinities and what trends we see in it across the periodic table. So again, we're going to define this. So we'll use our generic atom M that's not an actual element. But the electron affinity is, again, defined in the gas phase. The reason we are looking at gas phase is that then you don't have influence from other atoms or molecules that are nearby. So you're thinking about just the properties of just this single atom, isolated from everything else around it. Because other stuff around it can influence what will happen with these. So electron affinity, it's in the gas phase, and here we're adding an electron and turning that atom into the anion. Right, so electron affinities are all about forming anions, whereas ionization energies are about forming cations. And so electron affinities do not have, and again, we can define a second electron affinity and a third one, but generally we only think about the first one. Now, unlike ionization energies, which are all positive, electron affinities, which we'll call EA1, these can be negative, roughly 0, or positive. You can sort of have a range of different ones. For ionization energies, you always have to put in energy to pull off the electron. For electron affinities, for some elements, it's very easy to add an electron, and actually energy is released in the process. So this can be an exothermic process if you have a negative electron affinity. So a negative electron affinity means that the electron is highly attracted to the nucleus and is very stable there. So a large negative electron affinity is a sign that it's very easy to make the anion. Whereas a positive electron affinity means that the atom's sort of resisting having any extra electrons added to it. Now, the trends for electron affinity are not quite as clear, or I should say as obvious, consistent. That's the word I'm looking for. Not as consistent as ionization energies. So let's go and look at some data. So again, pull this chart over here, get out of full screen so I can make it bigger. But these are electron affinities in kilojoules per mole. So all these values are kilojoules per mole. So how much energy is either given off or how much energy does it take to force an electron onto an atom. So again, if it's negative, that means the electron releases energy when added. Or I should say the atom and electron. It's not really the electron releasing the energy, but I should just say energy is released in the process, meaning that it's favored, meaning that the atom likes forming an anion. A positive is the opposite. It takes energy, and it's unfavored. And it's possible to just have it be roughly neutral, which would be about 0. All right, let me just move this a little bit out of the way. Okay, and so we see examples of all these values. The first thing I'll point out is we can look at the noble gases. So helium down through radon, these are all positive. So this is again showing us that these have a very stable electron configuration, these noble gas configurations, and they don't want extra electrons added on because that's going to mess it up. So they don't like having electrons pulled off. They don't like having extra electrons shoved in, because it's going to fill the next shell, the next orbital out. And so all of the noble gases, for helium it's about 0, but everything else it's a slightly positive value. Whereas most of the rest, if you look at the table, are usually negative, with some exceptions. But we can see there is a trend that electron affinities do get less negative if we're again looking at this first column of the periodic table, or more positive for the other atom, for the noble gases. But they become less negative as we go from hydrogen down to cesium here on the left-hand side of the periodic table. So there is a tendency, though not as strong, that as we go down the table, we get an increase in electron affinity, or another way of saying this is it becomes less favored. And the clearest one we can see the column of atoms that really like to have an extra electron is number 17, the halogens. So everything in this block here you can see has very negative values, and it's highest towards the top. Again, it's not as clear of a trend, but fluorine, chlorine, and bromine here, here, and here All three of these really like to gain an extra electron. And as we know, these do form, like F minus is definitely the most common ion that we form. For the next column over, for oxygen, sulfur, selenium, we still see pretty negative values, but again, the trend is not as clear whether it increases or decreases going down the periodic table. But definitely from left to right, as we get closer and closer to having a noble gas configuration, the values become more negative. So as we go left to right, it becomes more negative until we get to the noble gases. Right? Once we reach the noble gases, then it becomes positive because they don't want to have an extra electron added in. So this is a general trend. You can see there's some weird things going on, like nitrogen has a slightly positive value. It doesn't really like having an extra electron. And this is, again, due to the fact that it has a half-filled p shell. You see things like beryllium has a value of about 0 because you're adding, going from having an empty p orbital to having 1 electron in p orbital and things like that. Same thing with magnesium. So the trends are not as clear-cut as for the other atomic size and ionic size and for ionization energies, but we still see some pretty obvious evidence for the for orbitals and things like that. Okay, so this is the last of the trends in the periodic table we're going to look at. So just a couple of videos today, and I hope you use any extra time you have to go ahead and review some of the previous videos about electron configurations. And again, at one point I want to just drive home here at the end is what drives all of these trends is the same for all of them, right? So for both atomic size, ionic size, and ionization energy, electron affinity, it's all about the size of the orbital, how far the electrons are away, and as we go down the periodic table, the electrons are further out, so that in electron affinity, as it gets added, it's not pulled on as hard by the nucleus, so that releases less energy. And as we go left to right across the periodic table, it's all about the change in effective nuclear charge. So as we go from left to right, the nucleus is able to pull more and more on the electrons as they get added into the same shell, but we have more positive charge in the nucleus. And so those electrons get pulled tighter, so they're harder to pull off or more favored to be added on in the case of electron affinity. And as we get to, and of course the special properties of the noble gases, right? That they get their electrons are pulled very tight, and we don't want to go into the next subshell. So that's why they have these positive electron affinities. All right, that concludes chapter 7.